So, Lecture 4.2, Diodes. Diodes are single-port nonlinear elements that approximately conduct current in only one direction. So that's like, when you think of a diode, that should be your first thought. Oh, it primarily just conducts current in one direction. And there are a lot of details that go into that, so that's what we will explore today. So we will consider the ubiquitous semiconductor diode, varieties of which include the light-emitting diode, LED, photodiode for light sensing, Schottky diode for fast switching, Zener Diode for voltage regulation. Those are some examples. Okay, so the model that we'll look at will be pretty good for those. See Figure 4.2 for corresponding circuit symbols. So 4.2 has them here. From left to right, this is the diode symbol. This is the LED symbol. So you've got like these arrows pointing out, like it's light emitting. And then this one is the light sensing, or the photodiode, Schottky, and the Zener. And there are others as well. But yeah, it's good to know at least a few of them just by a glance. In most cases, we use the diode to conduct current in one direction and block reverse current. When conducting current in its forward direction, it is said to have forward bias. When blocking current flow in its reverse direction, it is said to have reverse bias. If the reverse breakdown voltage is reached, current will flow in the reverse direction. So if you put it in reverse bias and you continue to increase the reverse bias voltage, at some point it will break down and flow current the wrong way across it. In most cases, this is not what you want. Okay. So it's important to check that a circuit design does not subject a diode to its breakdown voltage, except in special cases, for example, when using a Zener diode. Zener diodes are actually the one case where we actually like to operate them in breakdown voltage, but that's an exception and not the rule. So you're going to do a problem, I believe, in the homework on a Zener diode. So the Art of Electronics text talks more about Zener diodes. We're going to focus on the broader class, where we don't usually want them to be in reverse bias. Zener diodes follow all the same principles here, but we're actually going to operate them in breakdown, whereas we're going to assume in all of our analyses of other diodes that we're not going to operate them in breakdown. And at the end, when you've done your analysis, you should check to make sure that that's true. Because if you do subject a diode to its breakdown voltage, it's not going to behave in the way that you've assumed in your analysis. So typically at that point, you go back and you try to redesign the circuit so that you don't subject it to the breakdown voltage. Okay. We begin with a nonlinear model of the voltage-current relationship. There are a few symbols that we're going to use in this that we're going to define first. So let IS be the saturation current, typically about 10 to the minus 12 amps. So it's very small. And VTH be the thermal voltage. So it's equal to KBT over E, where KB is the Boltzmann constant, E is the fundamental charge, and T is the temperature, the diode temperature. It's the actual physical temperature of the diode. Okay. In most analyses, we just assume that those are going to be constant. although the temperature might change. And so it's important to remember that. We're assuming that the temperature is going to be constant, but in some cases you might need to take that into account. So here's the nonlinear diode model. Here's the equation. Of course, it's going to relate the current and the voltage. So the current through the diode is equal to IS times, I'm going to write EXP for exponential because there's kind of, I don't know, it's a little harder to read it if you don't. So VD over VTH. So e to the VD over VTH minus 1 is the equation. This is a D, not a 0, just so I'll rewrite it just to be clear. VD. So this is the diode voltage, and this is the diode current. And we almost always are going to choose the sign direction for a diode to be in the current flowing direction. So we assume a voltage drop in that direction. We assume a current flow in that direction. So that's the relationship between the voltage drop and the current flow. So it's an elemental equation like any other. Yeah, go ahead.
Just wanted to make sure that so the EXP is like E. Okay.
So it's like e to the x equals EXP of x. So this is kind of this is another way to write it, where you don't have to write it all in a superscript.
Okay.
Because it just gets small.
So that's like e to the VD divided by VTH.
Exactly. Yeah. So this is e to the VD over VTH. We just had a lot of subscripts, and so super and subscript. I try to avoid writing superscript and a subscript together because it gets really small. And I keep trying to go in and see if I need glasses. They keep telling me I have good vision, I don't need glasses, and I'm like, but I would look cool with glasses, so maybe I could still get them. Actually, I look like a dork with glasses. I tried them on, and I was like, yeah, no, I think I'm good. It's great. So, I aspire to one day look cool in glasses, so maybe. So this is the nonlinear diode model. It's an elemental equation like the others, like for the resistor, V equals IR. It relates the voltage and the current, right? But this one's nonlinear, and that kind of sucks because that means that if you only have resistors and transformers and diodes, you're going to end up with a nonlinear set of algebraic equations. Okay, but if you put in a capacitor or an inductor, then you're going to have a nonlinear differential equation, or a set of nonlinear differential equations. And those are no fun to solve. Most of them we actually don't have analytic solutions for. So that's not great. So when we have diodes in the circuit, we're going to end up with these nonlinear differential equations. And I don't expect you guys to be able to solve them analytically. And I actually won't expect you to solve them numerically either, although that is quite a bit easier. So solving them numerically using MATLAB, for instance, is relatively straightforward. You can get a nice simulation of the circuit. However, we're going to take a little bit of a different approach, and so we'll talk about that in just a moment. But I want to look at this nonlinear model a little bit first before we take a we're going to talk about a piecewise linear model. Let's get familiar with what the nonlinear model looks like. So 4.3 shows the nonlinear model. And so this is a VI diagram, okay? So the voltage across the diode and the current through the diode. So if you have negative voltage that's going across the diode, meaning that it's in reverse bias, then no current flows, okay? And actually, in real diodes, current doesn't flow until you put about 0.6 volts across it, okay? So you have to go put about positive 0.6 volts across it before it's going to actually start to flow current. And then it doesn't just like open up the floodgates completely, but it does pretty rapidly open up the floodgates. So at that point, when you start to go to higher voltages, so even at 0.65 volts, you can flow 100 milliamps. At 0.7, we're already off the graph. So over an amp flows through it when you put a voltage drop of 0.7 volts. So this thing starts to flow current pretty rapidly once you start to put positive voltage drops across it. So we're going to approximate that with this piecewise linear model, where we're going to say it's 0, and then at 0.6 it's going to have this linear slope, which allows us to use the techniques that we know, our linear techniques. It's not great because, I mean, this might be an okay approximation in a certain region, but when you leave this region, so this linear approximation is going to get really bad, right? Because that exponential will grow very rapidly, and that linear one is just going to keep going straight. So the piecewise linear model can be effective, and we'll talk about its sort of it has a limited amount of use. So if you're going to work around an operating point where the current is going to stay approximately steady, you'll be fine. But if you try to go and use this a piecewise linear model for a very wide range of current and voltage, it's not going to be very effective. So not going to be very accurate. So one can analyze circuits with diodes using the methods of Chapter 2 and equation 4.1 as the diode's elemental equation. A nonlinear set of equations results, which typically require numerical solution techniques. So we're going to sort of take a different approach. An ideal diode is one that is a perfect insulator, okay? When for VD less than 0. So if you have if you're operating in reverse bias, it's a perfect insulator. There's no current flowing through it. But then if you flip it and you have a positive voltage across it, then it's a perfect conductor. That's an ideal diode. And so we're going to use this filled in diode symbol to represent this ideal diode. So this one would look like, if you were to look at it on this graph, an ideal diode would conduct 0 amps up until whenever you have a negative voltage across it. But then as soon as you have a positive voltage across it, so as soon as it started to try to go positive, it would then conduct infinite current. It would just give you all the current that you want as soon as you flip voltage across it. You wouldn't be able to hold a voltage across it, an ideal diode, because as soon as you actually applied voltage, it would be a perfect conducting wire and it would short it out, right? So that is the ideal diode, but we can't build those. We only build things that look more like the blue line, okay? So what we're going to do is we're going to use this ideal diode concept, and we're gonna build a piecewise linear model using it and a resistor, and then you notice this voltage drop that is between 0 and 0.6 volts. We're gonna have to use a shift in voltage as well. So that's what we'll do here. This is a non-standard usage of the filled in versus not filled in most contexts doesn't have a lot of significance. I'm using that fact so that I can differentiate between the two. So in our context, but not outside of our context. In our context, we'll say that this is an ideal diode, the filled in ones. And the non-filled in symbol is a real diode, okay? Okay. So, great. So at times, the ideal diode is sufficient to model a diode. Often, however, we prefer a more accurate model that is piecewise linear. So, I mean, this is, we saw the nonlinear equation, which is a pretty good model, but it doesn't actually take into account the breakdown voltage. So if you kept taking the blue line back here to way negative voltage, you did one of those breaks in the graph, and you're at like, I don't know, it's like sometimes negative hundreds of volts, like 200 volts negative. That blue line drops off again. Okay, so it stays flat until a huge negative voltage, and that breakdown it falls off again. So even the nonlinear model that we have doesn't take that into account. So this function doesn't ever do that, right? So it's just approximate too. So what we're doing is we're approximating the nonlinear model, but even it's not, with a nonlinear model, it's not even perfect. The nonlinear model is not perfect. The ideal model is definitely not perfect. And we're going to go with the piecewise linear model, which is also not perfect. It's in between those two. So there are trade-offs. And you could write a function that actually had this breakdown in it as well. And you could use that in your equations, and then you wouldn't have to go back and check, did they break down, unless you wanted to maybe redesign. But you would know that your results were correct. So this is the thing that comes up a lot. And so in electronics, sometimes this gets hidden from us because electronic components tend to operate pretty well in the way that we write the equations. So resistor, Ohm's law, it's pretty good. And the capacitor equation is pretty good. The inductor equation, pretty good. But we can get sometimes a false sense of like, this is what happens, like this is like a physical law. But it's really a model, it's an approximation of what actually will happen. And in electronics, our models are pretty good. In mechanical components, which we're going to get to soon, the models tend to be, there are more and more complexities that come in, and it becomes harder and harder to get an accurate model of the mechanical system. So we're going to be doing the same thing. We're going to come up with equations that try to describe the behavior, but they're always approximate. They're never perfect, unless you're working with a in very idealized situations at zero temperature and these sorts of things, or down at the atomic level or quantum mechanical level. But those are always probabilistic. So Nothing's ever deterministically perfect in our modeling. So it's just something to keep in mind. So we talk about these. We have these equations. It's like we started off with the nonlinear one, and we're not going to use that most of the time. We're going to use this piecewise linear one. But keep in mind the nonlinear one wasn't perfect either. It's an approximation as well. But we can do a surprising amount of stuff with these approximations. These approximations get us a lot of bang for our buck, so that's good. So, okay. A piecewise linear model is shown in figure 4.5. It includes an ideal diode in series with a fixed voltage drop of 0.6 volts and a resistor with resistance RD. So, we've got an ideal diode we have this it's just essentially a battery. It's a DC source, right, with a fixed 0.6 volts across it. And that's there just to shift us over. So if you didn't have the resistor there, if you just had the ideal diode and the shift, we would have just moved this over to here with that 0.6, okay? That source just gets us to there. So that's a start, okay? You got the 0.6 volts. And now we recognize that, well, it doesn't immediately just conduct after you go above 0.6 drop. It starts to conduct more slowly, and then it ramps up. So instead of using the nonlinear model, we're going to use a piecewise linear model, and in order to do that, we can actually just put in a resistor. Effectively, this slope is governed by the value of a resistance in series, and that's what RD will be. So RD. So this approximates the nonlinear model with two linear approximations. So the off portion, so we're going to have ID equals, so 0 for VD less than or equal to 0.6 volts. Okay, so if VD is less than or equal to 0.6, we're going to say it's just 0. It's not conducting at all. Okay? And then when we get above 0.6 volts, the equation will be VD minus 0.6 volts divided by RD. For VD greater than 0.6 volts. So the slope of our linear approximation then, what's the slope? It's 1 over RD, right? Yeah, 1 over RD. Cool. So we already looked at the plot of the function. The slope in forward bias is 1 over RD. The model's effectiveness is highly dependent on RD. So an operating point must be chosen, and RD chosen to match most closely with the nonlinear model near that operating point. So what we're saying is we're not going to be very accurate with this linear model most of the places that, most of this positive voltage, okay? But we will try to do the best we can by using a linear approximation around an operating point. So we're going to say, okay, if we choose RD such that, say, we operate around 0.6, I don't know, 0.66 or 0.67 volts, then maybe this is where we're going to be operating most of the time. Or, I don't know, right here. Then if we find our point where this is equal, then we'll choose our RD so that we go through that point. So it only is really very accurate when we're around that point, but at least it's pretty accurate there. So if we have a problem where we don't have wildly swinging VD and ID, then we can feel relatively confident in our results. Okay? So that's the idea. Okay. Good. So, method of assumed states. The method of assumed states is a method for using linear circuit analysis to analyze circuits with nonlinear components. Okay? So, we know how to do the linear analysis, and we want to be able to analyze these nonlinear circuits, and we want to use the same techniques that we've already come to love. The method is summarized in the following steps. Begin at an initial time t0. Okay, so t equals 0. 2, replace each diode in the circuit diagram. So this is applicable to other types of nonlinear circuits, but we only know diodes so far. So let's focus on that. So replace each diode in the circuit diagram with the piecewise linear diode model. So you can just go ahead and put this in there for each diode you see. Okay? Great. Proceed with the circuit analysis of Chapter 2, ignoring the elemental equations for the ideal diodes DI. So we're going to ignore them the first, when we first do this analysis. Your system of equations will have unknown ideal diode current ID1 and voltage VDI. So you don't write elemental equations for them. We're leaving them unknown for now. Simplify it to the extent possible. So we can write down all our KCL, our KVL, and go through the analysis as much as we can. And simplify to the extent possible is pretty, you gotta interpret like how simplified can you get with this, but do your best. And then guess the current state of each ideal diode, on or off, okay? So ideal diodes are nice because if you guess that the diode is on, then if it's on, then it's a perfect conductor, right? So the voltage drop across it is 0, and the current flow through it is greater than 0. So we have to assume that if the diode is on, it's conducting current in the positive direction, right? So this is an equation we can use now. So this is this is sort of used in lieu of an elemental equation for the diode. VD, whatever, VD1 for first diode, VD2 for second diode is equal to 0. And you can use that to simplify your equations down, right? And for each diode that is assumed to be off, we say there's no current flowing. So ID for that diode is 0, and we have assumed that the voltage drop is negative across it. Okay? For n diodes in the circuit, there are 2 to the n possibilities at each moment in time. Okay, so that becomes a lot. If you have a lot of diodes, that's a very large number of possibilities. So that's why we're saying don't just write all possibilities down to start. This is a method for solving it by hand, right? So we don't want to just exhaustively do everything. So there's only one possibility at each moment in time, right? There's only one way that they can be. They have to be one way or another way. So do your best to guess. Say at time equals 0, what direction will these things, will this one be in forward bias or not? And try to figure it out and try to guess and make these assumptions. And then go ahead and do your analysis. You've got enough equations now that you made these assumptions about which ones are on and which ones are off. You can plug in VD equals 0 and ID equals 0 where appropriate. Do your analysis and get your solution. Okay, get your current values of voltage and current for the whole circuit. Okay. If even one diode violates its assumption from above, you have to dismiss the results and return to step 4. Okay, so if you guessed wrong, you got to go back and guess which other ones are off and on. Okay, so the way to check is to check these conditions. If you get an ID that's negative, that's not satisfied. If you get a VD that's positive, that's not satisfied in these situations here. So if you assumed it was on and then you get a current that's not positive, that violates your assumption and you got to go back and guess something else. So it's an iterative method. And choose a different combination of assumed states. So, but you don't have to necessarily just do it randomly. Like, oh, I chose these ones, so now I'll choose another completely random set. You can, but you can try to guess better this time. Okay, using a little bit of intuition, but also using the fact that you had certain of these diodes' assumptions violated, right? So it makes sense to try flipping the ones that were violated, right? So if you only had one that was violated, you have a pretty good chance of that working. If you had like 3 that were, all the conditions were violated on it, then if you switch all 3, it still might not work. You might have to switch just 2 of them, or what. So try to iterate down and to narrow it down. By hand, I'm not expecting you to do huge problems with 20 diodes or anything like that, because that's a huge amount of possibilities. The biggest problem I think that you're going to work is a 4 diode circuit, because the AC to DC conversion lab that you're going to do, you're going to use a full bridge rectifier circuit, which is 4 diodes. So you have to be able to go through the analysis with up to like about 4 diodes by hand. So, but with small circuits, it tends to be easier to figure out what state it should be in. These ones are going to be going forward, these ones are going to be going negative, or they'll be off. These ones will be on, these ones will be off. And you can guess correctly the first time, so you don't have to iterate a bunch. Okay, so say you got it right. So if not even one diode violates its assumptions, so these were the assumptions, we were good. All the currents, we assumed that they were flowing positive, they're all flowing positive in the result. All of the voltages, we said were going to be negative, because we were going to say that diode's off. That was true too. Then we are good to go, and this is the correct solution for this moment in time. So that we started out at time equals 0, right? So just for the initial time when we're trying to get a current state of the diodes, all right? So step 7 is this solution is valid for as long as its assumptions are valid. So march it forward in time, your solution. You don't have to go back and redo it for every moment in time. There are an infinite number of moments in time. If you had to do that, you'd be doing it forever, right? But you can march it forward in time until it violates the assumption. So do that, and then if one of your assumptions, for instance, if you march it forward for 30 milliseconds, and then this assumption is no longer satisfied, it flips. So that one diode that was supposed to be off is now on. And so now you've got to do a new, you got to go back to step 4 again, flip the diode, make sure your assumptions are met again, march it forward, so then it's valid, march it forward again in time until it's no longer valid again. Okay? So it's intimidating in the amount of stuff that you might have to do, right? Because if there's a lot of diodes, you might have to do this for a while. But it is a deterministic process. It might just take a while, right? So that's the solution method that I want you guys to use for diode circuits. Since impedance methods are valid only for linear circuits, steady-state analyses should proceed with the same process outlined above. Okay, so we can't go back to impedance methods because these are nonlinear circuits. Okay, so we're going to use the same process for steady-state analysis, 1 through 7 here. With a periodic input, a periodic steady-state solution may emerge. So you can have, if you have a periodic input to the circuit, say it's a sinusoid, which is what's going to happen with a AC to DC conversion problem that we're going to do. We have a sinusoidal input that we're going to want to convert to a DC output, right? That in steady state, you can't really count on a sinusoid coming out of a nonlinear circuit. And in fact, if you have diodes in there, it almost certainly won't be linear. It won't be sinusoidal. So all that impedance stuff is just gone for us here. So we got to go back to this method. And what happens is as we march it forward in time, we might see a periodic waveform emerge. Okay. So you go through and you see, it goes, for the input, in this condition, it behaves like this, and then for the input in that condition, it behaves like this, and it just repeats over and over again. So that's what we're going to do for our steady-state analysis with diodes in our circuits. So we don't have time to go through this example. It's a pretty involved example. I will go through it in detail on Friday. But the half-wave rectifier is the beginning of AC to DC conversion. Okay, so it only has one diode in it, but the full wave bridge rectifier that you guys will use in the lab is going to have 4. But the same sort of principles are going to apply. So when you've got a sinusoid with positive voltage applying here, current will flow, and you're going to get a voltage drop across R. When you have the negative half of the wave, though, from the source, it's going to shut this off, right? And you're going to have no current flowing through R. And so you're going to start to get a chopped a half wave out. And we're going to talk about what that looks like. We're going to go through the detailed analysis using the method of assumed states, and then we're going to graph it and just become really comfortable with this way of doing it. And it's a very simple problem, but the same approach can be used when we move forward to the more complicated systems. Okay, and I will, so we've got a couple minutes, and I'm not going to do the example. I will say that these types of problems, nonlinear circuits with diodes in them, these are the types of problems that start to lend themselves to simulation. Okay, so simulation can be done using the nonlinear equations, and using the same methods that we start with, we can write all the equations down, but then instead of solving the differential equation ourselves manually, we will plug that into MATLAB, say, and we will run a simulation. We will use the MATLAB solvers to simulate in time what the circuit will do. So that's sort of where things tend to go with these nonlinear circuits that are pretty complicated. But for simple ones, we want to be able to get an intuition for what would happen in the circuit. And we want to be able to analyze them on paper to a point, like not, with, even like 10 diodes, it's, there are 2 to the 10 possible states. So that's a lot, right, at any moment in time. So it explodes very quickly, and the methods that we're learning here, this process, is really only useful for small problems. But it is useful, and it allows us to gain an intuition of how the circuit's working. And that's what we're really going after with these nonlinear circuits. We're trying to get an intuition for them. We're trying to develop some basic techniques to do a simple analysis for just one component or 2 components. And that gives us the intuition for a larger system and what we could do with these components. Okay? All right. So Friday we'll go through this half-wave rectifier problem.